I think we're being recorded. By the way, there's no wrong answers. There's no bad questions. So you can say whatever you want. Yeah. Moisture management. So when we think of energy, it's, well, let's get an air barrier in Alaska or maybe even in Seattle, but go down south, who cares? Well, if you are concerned about your building, the number one place you would ever want an air barrier in your building is in Miami, Florida, or Houston, Texas, because it's the moisture coming from the outside into your building. Now, air barriers have been around forever. One of the presentations I show you a cave. Great air barrier on 5 sides. 6th side sucks because it's just a hole in the wall type of thing. And if you go through history, we've always tried to keep air out for comforts and for a bunch of things. So that's been there. We just haven't really done it. The first air barrier codes in North America was the Canadians, and they had a requirement in the code in 1990. And in that time, in the National Building Code of Canada, you could not talk about anything except life safety. So it was moisture management, and it was degradation of the walls and so on. Okay, I'll speak up too. Hopefully that's better. So that was the whole reason why we have air barriers, was moisture management, and saving energy was just a sort of plus. But we worked a lot with the Oak Ridge National Laboratories and the Department of Energy, and of course they were interested about energy out there. So anyway, we ended up in 2006 starting to be in the, oh brother. We are being recorded. So in the options, even back in 2006, there was 3 options. We still have 3 options today. So one is we need an airtight material. So you can be on a construction site, a loaded drywall gypsum board can show up on the job site, and you've met the code requirement. Okay, you haven't even installed it. Well, I'll show you some things you have to. And then we said, well, wait a minute, we need pieces to stick together. Because you can put big pieces on, but the holes are in the penetrations and the cracks and the connections and so on. So we need means to bring this together. So we developed, well, first of all, we developed the material test, then we developed an assembly test, and I'll show you why that's so important. And then we have the system test, which is the whole building. Now, testing whole buildings has been around for a long period of time. Washington State has put a mandatory requirement to test buildings. A few years ago, you had to test it, report it, still not working. Oh. Try that one. The importance of the system is that's the only way whether you know the air barrier has been installed properly. Everything else is done in the lab. And you get this list of things that you should do when you're an installer, but you can't see air leaks. So whole building testing is really, really critical. We actually are piloting a training and certification course here in Seattle this week for blower door technicians. And the reason for it is every time I talk to code officials or design professionals or owners, yeah, who's going to test my building? How do I know that person has the qualifications? So we answered. We developed a training program. We developed a certification program in accordance with 17024, and that is the answer back to those people there. So that's the most important thing. Okay, somebody else is complaining about me. I'm going to try and talk a little bit louder then. How do we do that? There. So if we go into the IECC, which is, by the way, changed from a code to a standard. It's now a standard similar to ASHRAE. And you can see that here's the E2178, but they also said there's 16 materials that are out there already that you don't have to do any testing. They're just grandfathered in or accepted as airtight and so on. And the same thing with the assemblies. Now we got E2357. 1677 is a half specification, half test method, half whatever it is. It's not a good written document. And the worst one is E283. Anybody have any familiarity with 283? It's referenced in the other two standards. It's referenced in 2357, but if you read it, and I'm oversimplifying, it says, pick a specimen, should be 2 stories high, pick a pressure difference that you want to test, pick something else. There is no requirements. It's impossible to fail the test because there is no requirements. You can do anything that you want. So that was put in there as part of the politics and codes, and it should be removed and on. And then we get the whole building test. And most of the standards, or most of the codes out there reference E779. It's the most common one. I'll show you what we're starting to get into the codes, including here in Washington State. So you get this whole list of materials. You can, as long as you use these materials, you meet the code. You don't have to have a test report. You don't have to have anything. And some of it makes sense. I mean, cast in place concrete is an air barrier. There's no question. Steel, glass. Some of the other things, you got to be a little bit careful. There's an issue with OSB where they changed, there's 2 glues that's used in construction, formaldehyde and isocyanurate. And sometimes they change the formulation or how much they put in. And sometimes then the air leakage through the material is greater than what is allowed by being called an air barrier. So I think all those things should be tested just to make sure, because different manufacturers have different manufacturing processes, and you may or may not. Now we're talking about 0.004 cubic feet per square foot at a pressure difference 1.57. We're talking really, really small numbers out there. Now, I said if you had a truckload of gypsum board come on the job site, you've met the code. Well, they have a few other things. So that's actual wordings out of the IECC. And the big thing is we have to make it continuous. And that's what we're talking about, the joints, the seams, the penetrations, the terminations, and so on. And that's where Joe or Sally or Jose or whatever it is, at 6 o'clock in the morning on a project, it's what they do. You got to remember, you can't see air leakage. And it's important because we were formed back in 2000 for that reason. The Commonwealth of Massachusetts had decided to put air barriers in their codes. Wagner Nice was a proponent of it. He saw the benefits of air barriers and so on. And after 3 separate years of seminars and talking about and so on, it was announced July 1st of 2001, air barriers will be in the code. And everybody is clapping each other in the back and high-fiving and all the rest of the stuff. And then some downer says, who's going to install this stuff? And everybody looked at each other and go, holy crap, we got to do something about it. And there was a meeting organized. We had manufacturers there, contractors there, design professionals, organized labor, sort of the whole industry. And they decided the way to deal with it is to form an association, and we can make sure that the installers know what they're doing. That's our whole reason to be around. Nothing's changed. That's still our reason to be around. Now we've expanded a lot. And ASHRAE 90.1 is a standard, but a lot of places it's either an option or it's mandatory for commercial buildings. And it has very similar types of things. And the latest version, and there is amendments to ASHRAE 90.1 on an ongoing basis. It's republished every 3 years, but in terms there can be changes. It's on continuous maintenance. So you're going to see a lot of changes if you haven't looked at ASHRAE, the latest version, on there. And there's a big emphasis to having whole building testing there. But you have similar things. The differences are underlined. So they have 13 materials. They've added in 1680, ASTM E1680, which is a roofing assembly test for metal roofs. There's also one for low slopes, D8052. That's starting to get in the code. And then they have E1827, again, which is a blower door, testing a whole building using an orifice blower door. So pretty similar, and there's exceptions on there. Here's a list of materials. Open cell foam, they didn't agree. Fully grouted concrete block masonry, didn't agree. Not sure why they struck aluminum on there, and then solid or hollow masonry they struck. So ASHRAE 90.1 doesn't give them an automatic pass. You need to do the testing on that. Now, when we get to the whole building testing, some of the exceptions in ASHRAE was over 50,000 square feet. You don't have to do a test. You can sometimes do partial tests. That's one of the issues we're dealing here with Washington State. Do you have to test every unit, or do you can test the whole building and so on? And then you basically don't have, well, you kind of have to meet it, but you don't have to meet it because they want 0.4. I think in Washington State, we're at 0.3 right now. So they want 0.4, but if you're over 0.4 but less than 0.3, you got to go see where the leaks are and try and fix them, and you go home. So there's nothing really stopping you from proceeding. Washington State is sort of a leader in the fact that you don't get your occupancy permit if you don't get your number. Pretty simple. And the other thing that's happened with the industry in general, but because we're dealing with walls, a lot of cases for air barriers and water resistant barriers and so on, NFPA 285. So if we go back, I'm going to say 10 years, NFPA was always around, but it basically applied to cellular plastic. So if you're going to put extruded polystyrene or polyisocyanate or expanded and so on a building, then you had to conduct it NFPA 285. And then the people that are really doing the testing developed NFPA 285 and so on. They really pushed for it. Well, we're putting a bunch of stuff on our walls, and this air barrier stuff is coming out, and that's going to add to the combustibility. So they put a requirement in the code, or they expanded the requirements. And pretty well today, most states in their local code have a requirement for testing wall assemblies. The only downside with testing wall assemblies or testing any assembly is that technically if you change anything at all, you got to retest. This test will set you back about $50,000, maybe even $60,000. So it's not something that you want to have to do. Even in some of the assembly tests, the wall assembly tests for air barriers and so on, that would probably run you, $10,000 or $12,000 to do that test. So you don't want to have to redo them. So you get engineering judgments. They basically say you test a wall, and then you get an expert in fire that comes along and says, we'll do a cone calorimetry test on a particular material. We'll compare that to the material that you tested, and if it's pretty close or it's better, then we will say we'll write you a letter that you can give to the code official and say this is okay. And there's a lot of discussion about how far should they go and when do you cross the line where you should retest and so on and so forth. But it's, and fire is something we want to be conscious of, no question. But then becomes a balance. The city of New York put a bunch of requirements in for fire blocking and wall assemblies, mandatory every 10 feet basically. And the issue came, or the industry felt that they weren't consulted, because once you do that, then you're stopping a lot of water in your wall. And you don't have the ability to have a rain screen principle. All the drainage that you originally designed into your wall is no longer there. You got to now have weep holes if you have masonry veneer to get the water to the outside all over your building. So we got to try and balance health and safety by building a building that's going to be high performing and it's going to last. And that's not necessarily easy. So back in 2009 is really where they put the expansion on what type of buildings that are subject to NFPA 285. And there was a pushback from the industry, especially materials that were very thin and didn't really add to the fire content. And so they went back to the codes and said, this is not fair. We're not really changing anything. Yes, our material may be combustible, but the amount that it contributes to the fire is very minimal. So then in 2012, you had a lot more situations that you don't have to do NFPA 285. And there's different types of the buildings that are exempted. Single story residential, for example, typically never has to do that. There's some 3 stories and less that you don't have to do it. It gets into quite complex, but at least they relax the things. You do a cone calorimeter test, and if you are this number or less in the code, you're okay. You don't have to do the test. Now we get into the materials and the test methods for the materials. And this is what I see in a lot of cases across the United States is you go to the manufacturer and the manufacturer says, yeah, here's the material, here's the testing and done, it's great. And you say, okay, salesman said it's great, it's got to be true, right? But you really need to take a look at what is important to your building and what is the performance level of all the materials that are out there. And there's a lot of good materials. We generally don't see a problem with materials on a job site. Most of the manufacturers out there do a really good job. The problems always end up going back to the installer. If they're not installing any material, the best material in the world, if they're not installing it properly, it's not going to work. And fortunately for the manufacturers, they're the first persons that people call. Your material isn't working. Well, you got these big holes that your installer left in there. What do you expect? So air barriers, and most air barriers are more than just an air barrier. They could be a vapor retarder, they could be a water resistant barrier, and so on. There's some strictly air barriers, but it's pretty simple. These are the qualifications to be an air barrier material. Air impermeability. Now, don't get confused with water vapor transport. We're talking about air going through the material, air leakage rate in the material. It needs to be continuous. Well, you can't do that with the material. You got to do that on the construction site. So that's an installation issue. It has to be strong. So why do we have, let's say, flexible materials out there, very thin materials? Sometimes you see them flapping in the wind. That's not strong. But why is that an acceptable solution? What do we do with most air barrier materials? Yeah, exactly. So if you have a fluid applied spray foam, self-adhered and so on, we stick it to buildings. And so somebody has a wind engineer that's designed that building for both the exterior sheathing and the framing and everything to withstand whatever it's supposed to withstand. And so the materials pass because all you had to do is stick them on. So that's why pull adhesion is one of the requirements that we have our installers do on the site to make sure the installation has been done properly. And then we get durability. Now that's a bit of an open question. We've worked on a durability standard at ASTM, I'm going to say 6 years, somewhere in that range, and we can't get consensus on what should we do. And a lot of the things, it's really hard to do a small scale test. Accelerated aging, sometimes we use that word to predict how long it's going to be out there. So if I put it through heat, UV, heat, moisture, freeze thaw, and so on for, let's pick a number out of the air, 50 cycles, what does that mean? Well, it means it went through all those tests. Does that mean it's going to last 5 years, 50 years, 100 years? And a lot of times I hear people talking about, well, we need the building to last 25 years because that's the length of the mortgage, 50 years. In fact, some buildings have been built for 5 years, and there was a particular reason. It was guy was going to build a really nice casino, but he wanted cash flow, so he built a crappy building, which he tore down in 5 years and then built his big one. That makes sense. But we also build crappy buildings that we hope will last for a long period of time. And I always go back to, think of if you have a house, you own a house, how long do you want your house to be around? The house that I live in was about 20 years old. I've been there for 23 years, probably there for another 5 years, and I want to sell it. And I'll guarantee you the person that buys my house is going to want it for 30, 40, 50 years. So we've got to quit talking about 5 years, 15 years, 20 years, whatever it is. We got to start talking about 100 years, 200 years. And if you think that way, then you start to look at it at a broader perspective. It's not something that you just slap up. Now, you got to do the maintenance, and you're going to have to replace the shingles, and the hot water tank's going to go and so on. But you understand that. But you still build the building envelope, which is really the critical part, so it's going to last a long period of time. And there's no reason why it can't, if we can keep the moisture out of there and so on and so forth. So pretty simple. Now, when we get to the impermeable materials, we really just create a pressure difference. Now, when we started in 2001, the test was from the textile industry, and we tested a 3/4 inch by 3/4 inch piece of material. Now, the requirement is 0.00, maximum 0.004 cubic feet per square foot at a pressure difference of 75 pascals, 0.3 inches of water, 1.57. So what do you think the accuracy of that test was? Yeah. So, and the other thing is we've learned homogeneous materials aren't homogeneous. There's always some differences in. So this is 1 meter by 1 meter because testing laboratories use metric, or 39 inches by 39 inches. And the other thing with this test method, because we say 75 pascals, everybody thinks we test at 75 pascals. You never do that. You always have multiple tests, whether it's a whole building test, this test, and you report at 75. So there is some site testing that ramps, it's called a posi tester. It's a cone shape, and you can find leaks on brick ties in small areas. It goes up to 500 pascals. And so there's been pushback. Well, you can't do that. The leak that you're showing on the building is because you're using 500 pascals. You should be using a 75. That's wrong. In this particular case, the 500 pascals is required for the soap solution that's been specifically designed. And so if you run it at 75 pascals, the viscosity of the soap solution is heavy, and you could have a leak and it'll never show up. So you got to understand to go past and understand why you have this. So there's this goes up to 300 pascals, 25, 50, 75, 150, and 300, but we reported at 75. You always get that curve when you're doing testing. So pretty straightforward. Every testing laboratory had to build this apparatus because the apparatuses that they had before were used to testing not 0.004, but 2, 3, 10 cubic feet per minute. And so the accuracy of that test was just out the window. So everybody's got it. They had to pay for the mass flow meters and so on. And the most important part of this whole thing is the mass flow meters. Okay? And that's just a little agent. It's going to cost you about $6,000 each, and you need at least 4 of them to do proper testing and so on. And it contains a material, it's measuring mass flow, contains a material that sometimes Homeland Security wants to know why you want them. But it's been used. We do 5 specimens and so on. Pretty established out there. My next presentation, I'm going to talk about this slide. So I'm not going to cover it now, but any guesses of what it is? It's an air barrier material. Yeah. And it's fluid applied, so you're both right. So I'll cover that. There's a whole reason to do that. And then we get into continuous. Picture yourself on this construction site, and you're going to put the air barrier on the wall, and you want to make the roof connection. And how are you going to do that? Yeah, really good question. Questions that you should ask before you start your job, that's for sure. And we do have in the codes requirements for this. So why do we have transition membranes? How do we make that connection? Why do they have to be flexible? Exactly. We got settlement and we got expansion and contraction. Some materials, wood will swell when it gets more moisture into it. Buildings move all over the place. They also flex too. I was at a conference in first week in August, and RDH, which is they have an office out here, we're showing the testing that they do for building movement. It's really cool. And it's amazing how much your building actually sways if you got a tall building out there. But we have identified, even in the code, here's your biggest leakage areas. Number one is walls to roof. And what we see is that the subtrade that does the wall, they stop at the top of the wall. The roofing stops at the edge of the roof. And Andrew has a presentation that he calls by others, because that's generally on the prints is by others. So you want to start a new business, get automatic business because you can prove it's you. Just have the name by others. And you can point to it and say, I'm in that spec. My name's in there. The second biggest leakage area is the windows to wall, and that's because who make the connection? In commercial construction, most of the time the windows are not installed. So we wrap the air barrier into the window. The window installer comes along, and his job in his mind is square and plumb and secure. Couldn't care less about flashing, couldn't care less about air leakage. So who makes the connection? So maybe somebody grabs a bat of fiberglass and stuffs it around the window and goes home. So that connection becomes really, really critical. And you got to keep in mind too, going back to why you need flexible, think of a CMU wall or concrete wall. How much does that move? Very little. Put an aluminum frame window in it, that aluminum frame is going to move all over the place depending on the temperatures that's out there. Here's a penetration that's sealed, and it's done an excellent job. What you can't see is 5 different pieces behind that fluid applied material, because that pipe will move back and forth. It's going to depend on the length of the pipe and where it's secured. If it's a really short pipe, it's not going to move very much, and if it's floating, but if you have 20-foot pipe and it's secured at the other end and this end moves back and forth, you're going to have a lot of movement out there. And we go through, we're actually running a training course for installers this week, and we run the installers all the way through that, and then we're starting to get back to hands-on practicum during a training course. During COVID, we couldn't do that, and so they have to figure out how to do all these transition membranes all over. So here's the assembly test, and we started out with a piece of material, and we found that it was airtight, and that's great. And then we started to look at, well, where's the problems? Well, the material has to stick to itself unless you're doing fluid applied. Then you have to have all your transition membranes. And then we subject this to, we call it conditioning. It's actually beating it up. And then we do the air leakage. So we use the common square penetration, round penetration, electrical outlets, and a blanked-in window. And so the manufacturer has a base wall that they start with. It can be wood framed, steel framed, or CMU. It doesn't make any difference. And then they put the material on and they put the accessories on. Now, back in early 2002 to 2006, when we talked to the manufacturers and said, we need to know what caulking, what strips, what's your transition membrane, all the what we call the accessory materials, that goes with your material. And the response I would generally get from the manufacturer is, drop dead, I only make the material. It's up to you to figure out how you put it together. And I'm overemphasizing that, but they did come around, and they had a common question, I guess you'd call it. I don't make that stuff, so why should I be responsible for all the things that needs to be used to have my material stick together? And the answer is because you need your material to stick together. So every manufacturer will have a list of accessories. It could be caulking, it could be strips of material, it could be a whole bunch of stuff that they agree and approve for use with their material. So that's the most important part. That's where the contractor now has a running chance to do the job properly, because he now knows what he can use. Otherwise, and even with a lot of manufacturers, when they took their wall into test, they thought, what's air barrier? Just stick some stuff on the wall. In one case, the whole wall blew apart because the guy hadn't fastened the drywall properly to the steel studs. So everything blew apart, but it's not unusual to have everything open up. A good example is the flexible membranes. A bunch of manufacturers out there. There's a lot of use in this area. And you just take a piece of tape and stick it over, so that seals it. Well, we go up to 1,200 pascals pressure difference when we're testing it. Those seams are gone, completely open. And again, the reason why that we needed that out there. Here's an example of one being done. It's fluid applied asphalt type of base. You can see the openings for the window being installed on there, and then that's subject to the pressure difference. Now, the other part to be strong is it's stuck to the wall. And so that gets away, but it's got to withstand not only wind pressure, but stacker pressure and mechanical effect. And those can be combined. So here's a typical stack effect. You've got air moving within the building. It's convection current. And just on that, How many in the room here agree that heat rises? Yeah. Okay, so if you go to a building science course or you look at physics, how does heat flow? From what to what? Hot to cold. Okay, you're 98.6, everybody, roughly. So you're an unvented combustion appliance. You're actually polluting the room by being here today. You're breathing, all things that you shouldn't do. But you're probably the warmest part in this whole room. So where does the heat from your body flow? Yeah? What do you think is the coldest part of this room, typically? The floor. In some cases, if you have heated floor, that's not going to work. But in most cases, the floor is the coldest part in the room. So heat from your body is going to go hot to cold. So heat doesn't rise. It'll always, that's the physics. It'll never change, and so on. And it's kind of cool if it gets really cold here, stand beside a window and then stand beside a wall and just feel the difference. Because you have a temperature difference that's greater in a window than you have in a wall. So if heat doesn't rise, then it's got to be hot air that rises, right? Because if we have a two-story house, generally go upstairs, it's the hottest part of the house, and so on and so forth. The problem is hot air doesn't rise. What happens, and why do we get hot air on the second floor or the top part of the building or near the ceiling, even in a room? We need something else. No, let's just think of in a building. Let's say it was really nice and warm, hot air at the ceiling. Why is the hot air up there and you down here in your cooler? That gets into air movement. It's actually even simpler. Hot air is less dense, and you need something that is more dense to push it up. So if this temperature in this room was exactly the same every inch, there would be no air movement. There would be no hot air at the ceiling. Have holes in our building so that cold air comes in, it's more dense, it displaces, it's the buoyancy effect. Light goes up, heavy stuff goes down. And so it really doesn't mean anything, but it helps you if you start thinking of the physics, it helps you to start understanding how our buildings work and so on out there. So, and has everybody been to a building science course? Yeah. I'll give you the Cole's notes of how you can become an expert in building science. You got to learn 2 words. Anybody want to guess what the 2 words are? No wrong answers, by the way, remember? 2 words and everybody will think you're a building science expert. It depends. Because it's actually true. Everything, it depends. We get to ask, what is the best air barrier I should put on my building? And we go, well, let's start with, where are you? What is your building? What is the interior conditions? And the list is about this long. So it is always, it depends. And this is durability. There's time and time again, buildings are sometimes bulldozed in worst case conditions, but a lot of times major repairs. And this is because we got air leakage into the buildings, into the building envelope, that it carries warm, moist air. And that could be coming from the outside down south and from the inside up here. And it condenses into liquid. And everybody thinks, well, there's a hole in the wall or a hole in the roof, but it's actually air leakage control. And that will cause corrosion and mold and mildew and so on. A good friend of mine in Minneapolis went out and looked at 5 buildings, 5 residential homes, wood-framed homes. And to make the story short, all the cladding had to come off. And when the cladding come off, and there was no evidence on the outside of moisture problems, but there was some testing done that showed high moisture content of the wood. So the cladding came off and the exterior sheathing, in a lot of cases, even the studs were rotten. had to be replaced. The average cost for these homes, they were quite large, was about $200,000. Okay? And there was no liquid water coming from the outside or anything. So when we went through the building analysis for it, is warm, moist air going into the stud cavities, condensating on the first plane of condensation, which happened to be the back of the OSB, and it rotted it from the inside out. The kicker was these homes are less than 5 years old. And I've seen some buildings in Toronto, they were building a 34-story building. They started repairing the first few floors before they even hit the 20th floor. So we could do better things. So the other thing that we came into problems when we started is, if I said air barriers in this room, everybody would think of something else. And so we had to get some terminology down. So I propose that air barrier is a verb. And if you wanted to noun, you got to add something to it. So we have air barrier materials, that's the big pieces, that's what the manufacturer sells. We have the accessories, whatever it needs to keep the big pieces together and to seal them to penetrations, terminations, and so on. Then we have components. And components is doors and windows and skylights and appendages and whatever. It's things that are determined to be airtight before they come to the job site. So our job as an air barrier contractor is to connect those things, but we don't do anything. We don't run extra beads of caulking or whatever it is. And then we put everything together in assembly. We're using the same terminology that we always use in construction: wall assemblies, roof assemblies, foundation assemblies, and so on. And then system is the whole building, all 6 sides. And that's a critical one because it's like trying to blow up a balloon or a paper bag with a hole in it. You're never going to do it. So you do a really fantastic job on the wall, and you think you have an air barrier in the roof, but you've got a roofing material, a water-resistant barrier that sheds water, but allows air to leak through it like crazy. So those are the types of things that you have to keep in mind. And again, that goes back to whole building testing. Excuse me. John's going to talk about waterproofing, and waterproofing is a water-resistant barrier, but it's also an air barrier, and it's part of the whole system. So if you take a look at those criteria and things like that, then, how do you get the answer what it is? So going back, and even today, ABAA is the only organization that published material specifications for air barrier materials and water-resistant barrier materials. There's none at ASTM yet, none at ASHRAE or any other of the SDOs that are out there. So we did that because we wanted to standardize things. You need to know as a design professional or an owner that the material that you're buying is going to work. You, in most cases, don't want to go through all the engineering that needs to be done and analysis to come up with something. So these are on our website. Evaluated assemblies, because part of even approving the material, they have to show that they can put it together in the assembly. So they have to test the 2178 for the material. They have to test to 82357 for the assembly. So you go on there and you can see the whole list. Here's 2 of them. One is S0008, which is fluid applied membranes. And the other one is S0010, self-adhered sheet membranes, bitumen based. And so when you go through, this is a standard specification. It tells you how to do the specimens and things like that. But the most important part is the testing. And we've just added in the last few years engineered polymer films for interior application. And we really don't want to use the word interior because we want to keep it neutral, because where you put your air barrier can be in the inside, outside, or in between. There's a whole design thing of establishing that. And it's basically a vapor barrier that the manufacturer says if there's high humidity on one side, it will become more vapor permeable, allow more vapor to go out. And my reaction is, well, every material changes if you change the atmosphere, so why is your material different? So on that particular one, there's 6 different tests to be done to determine the water vapor transmission at different atmospheres. And then that shows that it actually is working. And then fluid applied membranes was one that we did, non-insulating board stock. And what we're talking about there is, glass face gypsum board by itself, plywood, so on and so forth. And we're keep adding to these requirements that is out there. Now, developing the project spec, that gets right to the heart of what you guys are working with in most cases. And so because air barriers were relatively new, when we saw some of the specs that came out in 2006, even 2009, 2006, if I phoned you guys up in most cases and said, do you want to come to a seminar on air barriers? The standard response we got was a pause and what's an air barrier? I don't hear that anymore. Everybody's now saying, oh, of course, yes, we have to have air barriers, and oh, for sure, we got to have them in our buildings. And then they describe a vapor barrier. So we still got a lot of education to go. But anyway, this is getting, these are on our website. They're in Word, they're downloadable, they're free. You can modify them, but it gives you some guidance as to types of things that should be in there. It's a standard 3-part spec. And we just hired a spec writer to update them because some of our specs are a few years old. And we're hoping to have that done early by next year. We're hoping to have fluid applied and self-adhered out by the end of this year type of thing. So it'll always be on there. Standard 3-part spec. You can also go to a bunch of other organizations, Spec Link and so on. They're going to help you. We focus on the, the 5 control layers in a building. And specifically with air leakage and water resistance out there. So section 1, and probably you do this on a daily basis, so you probably won't see anything new here. It's what does all the applicable sections and so on. And you can get guidance from CSI as to how to write your specs and so on. The key there is, what are your other trades? So when we teach the installers, we say, before you can put your air barrier in the wall, it has to be clean, dry, sound, and smooth. WR Meadows does a good product. Vapor Shield does a good product. Would you guys put your material on this wall? Kevin? Why not? And this is a real picture. Now, it had a brick veneer on front of it, so I figure this is either, Friday before a long weekend or the Tuesday morning after a long weekend, but something was, and it's non-structural, so it was just basically a fill. And this is an extreme, but we did run in, when the error money was coming around in 2008, 2009, there was a lot of work done in schools. And up in New York, a lot of the schools were backup walls of masonry, CMU, and so on. And there was time and time again when the brick veneer came off and they were supposed to put a fluid applied on or something like this. It was not this bad, but pretty close. And so then you had to redo the backup wall before you could even put the air barrier on and things like that. So it was a big issue out there. Well, yeah, good question. I mean, you at least should have brick ties, or maybe they save money. Value engineered out. You can, my opinion of value engineering. So, and all the materials manufacturers, if they go through the evaluation process, they will typically put on their literature and things like that evaluated. So that gives you, can, if you want to, you can still go to the website and understand all the test methods that goes into it and why we made it a good material. We had a lot of pushback to start with, saying ABAA should only be interested in the air leakage rate of the material. Forget about elongation, compression, whatever it might be. That's the only test you should do. Therefore, in my next presentation, I'll go into why peanut butter, the slide of peanut butter is there. So it's not only, when we talk to architects and design professionals and so on and building owners, they wanted to come to one place and get an air barrier material and know that it's going to work. So to work means you have to have a quality material. So there's a bunch of other tests that you need to do to make sure your material is proper. One of the examples I use is spray foam. So what is the most important characteristic in spray foam? evolved? Elongation, compression, anything you can think of. Anybody want to guess? You guys are a tough crowd. It's dimensional stability, because spray foam is manufactured on the site. It's not manufactured in the plant. You get two chemicals, iso and resin, and the installer manufactures the material. He takes the two materials, puts them under pressure, heats them up, sprays them on the wall. Medium density will then expand 30 times. And if it's too hot, too cold, too high a pressure, too low a pressure, blockage in one line, so you get more iso or more resin instead of the 1-to-1 ratio, and you don't have a good material. And it's not stable. That's why we do the dimensional stability test, and it will crack. If it cracks, it's not an air barrier material. So every material will have their key part that's really critical for that material. And so that's why you end up with a list of tests that is done on the material to make sure that you, as users of the material, have all the information that you need that's out there. So again, your different materials, the specs that are out there. Compatibility, whether it's chemical, adhesively, or physical, is a big issue out there. And there has been attempts to come up with charts so you can just go down to, like you see here, and go, yeah, this is good. Be cautious. One manufacturer on one of the charts that's floating around out there said, this type of material, I do 6 different pieces that fits into this type of material. 3 of them, your chart is actually 100% correct. But the other 3 are not compatible. And yet I can put all those 6 under that one heading. So make sure you talk to the manufacturer, make sure that you understand what is going to be compatible, get a letter from them, preferably, so that you know which is compatible and which is not compatible. Now, and again, we're still in section 1, pre-construction meetings, testing mock-ups, whose goes first is really, really critical. I said in a meeting, I was asked to go to a meeting where the ABAA Quality Assurance Program was going to be part of the contract, and it was relatively new in that area, and the design professional said, I got you all together here, it's going to be ABAA, here's what they do. If you've got a complaint, say now, otherwise you're going to follow the rules. And so we had the discussion and so on, and we got into, and I said some of the things, who's doing the sequencing, do the sub-trades know how the surface, if it's CMU, do they understand the joints should be struck flush rather than concave tooled and so on. And that started a good discussion. And I thought the most important part of the whole conversation was when we finished, each of the sub-trades, and the particular one, the window fenestration guy turned to the air barrier contractor and says, we got to get together and we got to talk about who's going to do what and how we're going to make the connection. The best part of the whole meeting was getting that communication out there. And details, the old saying, devil's in the details. It really is critical in air barriers. You can't see air leakage, and a little hole, it's only a ½ an inch, like who cares? Well, that's a big leak. Section 2, you get in different materials. This is something we're trying to address, because if you go to our fluid applied spec, it's about 40 pages long. And I'm going to say somewhere around 20 to 25 pages is just simply, here's a material from this manufacturer, here's the air leakage rate, the water vapor transmission, and here's their accessory materials. It takes about a ½ a page. And so if you take a look at all the different materials now that become, that's one thing we're looking at is, can we just list all the materials and have all the details somewhere else? And we don't know if that's going to be good, bad, or indifferent, but that's what we're trying to look at to reduce the physical size of it. And then what are you using that material for? And what can that material do? So there's 2 parts. Can the material be another control layer? Does it have the physical properties that you want for water resistive or vapor retarder or whatever it might be? And then you have to design it. If you look around this room right now, I'm going to say you're going to see at least 10 air barrier materials, because they would be air impermeable. Doesn't mean that that is the air barrier in this building. So you got to have a material that can be an air barrier, and then does it want to be another control layer? Where are you placing in the building? And if it's an air barrier, how are you making it continuous? Okay, so it's not only getting there, but you can see these are all air barriers because they will stop air from going through the material. Vapor, maybe. Every material has a water vapor transmission rate. Every material will meet one of the 5 or 4 means. It depends on what you need, what you want, and so on. Keep in mind that every time the atmosphere changes, you get a different number. And then water-resistant barriers, all these, ones that wouldn't be a water-resistant barrier would be things like gypsum baseboard or OSB, or that should be logical. And then insulation, you've got to get into basically the cellular plastic. So it's board stock or spray foam or whatever it is. But you could have some material that can provide all 4. Spray polyurethane foam can be an air barrier, can be a class of vapor retarder. It can be a water-resistant barrier, and it can be a thermal barrier or a heat barrier, all 4. Other ones, not. And it doesn't necessarily mean that spray foam is that much better. A lot of times spray foam is put in for insulation purposes only. And it's not the air barrier, and it's not the vapor retarder, and it's not, all the other things that are out there. And then you get into your performance. And so the key one is the material performance requirements, vapor permeance, the assembly and accessories. You got to pull all those things together in there. Now, we in our project specifications give you recommendations. You can change them to whatever you want. A lot of people feel that they want a tighter building. They want different things, so you can go. We recommend for whole building testing. In fact, 0.4, I think, is out of date. ABAA should be promoting more tight buildings. It was proven here in Washington State that meeting 0.4 is actually pretty easy. You don't have to spend a lot of details on there. You're doing a really good job of having relatively good airtight buildings here. So it should be down, in my opinion, down around 0.15, 0.10. The Army Corps of Engineers, who we've worked with over the years, started out with 0.25. And this is probably 10 years ago. And everybody says, that's ridiculous. It can't be done. Nobody, this is stupid. The list went on and on forever. And what we saw as contractors, that's what he or she said in the first job. And the second job, they said, well, it's stupid, but okay. And then the third job, well, of course, everybody should be doing this. And I saw a slide, because the Army Corps does thousands of buildings, whether they're new or retrofit, and they tracked them over, I think it was a 10-year period, and there's literally thousands of dots, but there was a trend like this, absolutely no question. Now, we haven't changed the material, really. We haven't changed the design of buildings to the Army Corps buildings anyway. What's happened? People started to understand, how do we make a joint airtight? And so they're looking at going from 0.25 to 0.15 because all of their buildings are coming in less than 0.10. A good chunk of them are coming in at less 0.05, and one of them that I'm aware of came in at 0.03. That's nice, that's airtight. And that's simply just understanding how to do those. Whoops, I should. The options for 23, we don't think that's an option. We don't think whole building airtightness should be an option. That should be in your spec. Then you got to get into the supporting structure and so on and so forth, what you want there. Got to get into your fire characteristics, NFPA 285, whether it's appropriate. E84 or the tunnel test. There's a thing, they put flames on one end and see how far it goes down the material. It'll also give you a smoke index and so on. And then what other properties do you want? Is tensile good for you? Do you want sealability? Is that, what we talk about sealability is like a fastener sealability that you can drive a fastener through and it will seal to that material. And there's manufacturers out there that do a really good job of that. And there's manufacturers out there that claim they do a really good job. So you want to sort of separate those out. And then UV resistance is a big issue. We see time and time again, a really nice job of the air barrier, and then it sits for 2 years. And then they wonder why, the air barrier is falling apart there. This could be a whole week's discussion on vapor barriers. permeable or impermeable. First of all, I'd like to point out that at least in codes, there is no such thing as a permeable or impermeable vapor barrier. We call it vapor retarder out there. You could surmise that because the 3 classes goes up to 10 perms and anything above 10 perms is considered vapor permeable, but it's just misplaced. So I ask you to just look at the water vapor transmission rate. That's really what we're talking about. And we're finding that some cases you don't need a vapor barrier. Some cases you need a really good vapor barrier, but look at your building. It goes back to it depends. What are you trying to do with that building? How do you want it to perform? And when we started in 2000, most states, you had to have a vapor barrier, it had to be less than 1 perm. No questions asked. Commonwealth, Massachusetts had 0.1 perms everywhere. And you had to do that because that was the code. Now, if you read the code, there's lots of areas in the United States, you don't need a vapor barrier, or at least the code says. And if you think about it, it's pretty easy to understand if you go down to Houston and Miami and so on. Yeah, should have a vapor barrier. And where would we put the vapor barrier? What part of the wall? Outside, yeah, because we want to stop the water vapor from coming in. In Fargo, North Dakota, or Chicago, or Alaska, where do we put the vapor barrier? On the inside, makes sense. So I'm in South Carolina, where do I put my vapor barrier? Some people say put in the middle, and so on. But yeah, well, I would challenge you on that, but that's a whole nother day's story out there. But that's the issue. You know, it's really simple if we have extremes and so on. I mean, to me, the extreme for that is I did an inspection on a nitrogen storage tank where it's minus 40 all the time, 24 hours a day, 365 days a year. It had spray foam on the outside and a vapor barrier at one time, but that vapor barrier deteriorated. And so the moisture drive and that soaked the insulation. It all had to be taken off. And you could hardly lift what would be something you could pick up with your little finger. You could hardly lift it. So there is cases like that you have to have a vapor barrier. But in other cases, you could add problems. Because where's it going to dry to? Because that's what we're all about, right? We want our buildings to dry, so we want a high water vapor transmission rated material so our buildings can dry. Can't argue with that. Which direction are they drying? At what time of year? And one slide I use is, you guys are building buildings wrong. People wake up and, what do you say? And then I add at some time of the year. So, and again, I'm going to go to Chicago. You go there in the middle of the winter. We design our buildings because we consider it a cold climate. And so we do all those things. Ever been in Chicago in August? It is ridiculous. And the building is absolutely built wrong. Nobody can argue that. It's absolutely built wrong. So why aren't they falling down? Why don't we have major problems for every building in Chicago? Single. Because deterioration takes time. And it's like even if you have a flooded basement, you know, and if the water gets on, if you got drywall down there, and the drywall gets temporarily wet, but it dries right away, it's okay. And that's what happens to our building. So buildings are really, really complex, and we're building them. You know, we used to build out of sticks and mud and stone and so on, mass buildings and so on. Going to Europe, a building is 3,000 years old, and it's probably as good as it started. We're going to light gauge metal framing, materials that can't absorb moisture, can't hold them. They're not reservoirs. The office, the building that I have, where my office is over 100 years old. There's no air barrier, no vapor barrier, no thermal insulation, no water resistant barrier. Because I own the building, I sure hope it lasts for another 100 years. So why does my building work? 5 whites to brick. Okay, so that was designed in those years, and we knew how to build buildings. We're forgetting how to build buildings. So you got to go through all these things and so on. And in some cases, your decision will be, I will not need a vapor barrier. And then it could be simple. part of the one class of the vapor retarder the code requires is you're painting on the inside drywall. That's a vapor barrier in most cases. Most time you don't consider that. And so again, gets into where, if you're going to have a vapor barrier, where are you going to place it and what are the problems? That is not a simple subject. And then all your accessories you have there. Section 3 gets into what needs to be done. And there's some critical things that you want to put on there. Substrate, as we saw in that one picture, the substrate has to be clean, smooth, dry, and sound. Here's an example there. You can see the transition membranes around the windows, and this particular material, we talk about gap bridging, ability of material to bridge a gap. And if your material can't bridge a certain width of gap, then you've got to do some preparation to it. Could be just simply filling it with caulking, or if it's a bigger gap, you could use a backer rod and caulking over it and so on, but you need that. So the substrate preparation, and who is going to do that? Does the masonry contractor, if it's CMU, understand what is required? If it's a carpenter that's putting on your gypsum board or whatever it is, starting out is really critical. Think of putting air barriers on like painting. All the work is getting it ready. When you got it ready for painting, painting actually goes pretty quick here. Now, you need materials to bond to the substrates. You got the top picture there. You got a wide crack that nothing will span it without some treatment to it. You got a chunk of concrete missing there and so on. Most self-adhered membranes and some of the fluid applied membranes will allow you to have a crack of 1/4 inch, but talk to the manufacturers. Make sure you go to their tech data sheet for your installers on that. Mechanically attached, you're not as worried about some of the things on there, but you got to, again, have it smooth. If you're putting it on and you have something that's sticking out, that membrane is going to move back and forth. If it's a flexible membrane, and it will rub on anything and you'll end up with a hole and you don't have an air barrier. Board stock, if you're putting that on, if it's put right on the studs or on a backup wall, and if that's going to be your air barrier, you got to make sure that it's nice and smooth too, because construction isn't perfect. And so our walls are kind of out and so on. Sometimes we have something that will keep the board stock from going up nice and tight against the wall and so on. So preparation is critical on all of these things. And then the transitions. And Andrew's going to go through a lot of things on here, but you know, where is your air barrier on the roof? Might not be the roofing material. In fact, most cases it won't be your roofing material, because you can make a roof watertight because it sheds water. But if you take a look at your curbs around your mechanical equipment or pipes coming through the roof, they're all nice and flashed. They may have a curb to drain the water away, but there's a gap between the pipe or the duct and the opening. Because nobody wants to cut a hole in this roof and then, oh, wait a minute, I've got to move it over 1/4 inch. So we cut a bigger hole, sometimes a really big hole, to put a really small pipe in. Doesn't make sense. But those are the key things. And then where do you make that connection? And here we're showing the air and water resistant barrier, or the air barrier in this case, going underneath the insulation over top of the roof deck. What is the roof deck? Is it a Q deck? Do you have boards to go over that? We're taking it up over the parapet and down the other side. There's some key issues there on the design, because one of the problems you have with this design is, have you sealed this area here? Because if air is allowed to go up in here, yes, you got an airtight barrier across here. More moist air coming in here. In a cold climate, this will condensate and you'll have problems there. So be very, very clear. And again, you saw these before: roof to wall, foundation to wall, wall to door, et cetera, slab. How do you go from one wall to the next wall? That's the details that you have to make sure that everybody understands. And in a lot of cases, there has to be flexibility on the materials there. Installation, you follow the manufacturer's instructions, and sometimes it's pretty simple, and sometimes it can be pretty complex. This is showing a 2-component system. Any fluid applied, well, all materials are going to be subject to ambient conditions. You know, if it's -40 out there, there's pretty well nothing will work. But in the fluid applied, because they need to cure humidity and temperature, is going to have a big impact. that's out there. Make sure you understand that. And then you get into what is the adjacent materials from the walls to the foundation. If the waterproofing is your air and water resistant barrier for your foundation, how are you making that connection? You've got to do all 6 sides. And then the other thing is what happens when the trades come along after the air barrier installer is gone. Punches holes, puts pipes, puts conduit, or drives a forklift through, all those type of things. You know, who does what? One of the things we're working on is penetrations. Mosley Architects, south of Washington, D.C. has used ABAA in their projects for almost 20 years. And the question they gave me is, you know, I make sure my air barrier is done really good. And then I put stucco on, and I got 10,000 holes in it. Should I be worried? Yeah. But we don't have an answer to you of how you deal with that. So any cladding system is going to have adheres. That has to be sorted out. How are you making them airtight? And the manufacturers have, some of them have gaskets, some of them you wet seal, whatever it is, but make sure it's done. Curtain wall, window walls, those are a bit of a problem, and make sure somebody's looking at it. We've seen some drawings come out where you're to attach a transition membrane, and it's supposed to be up in this on the part of the window, and the gap is a 1/4 inch. Try and put your hand up there. You know, it just doesn't work. So you can draw it, but it doesn't mean that you can actually construct it out there. And then the quality control. So any ABAA project, we send an auditor out. There's at least one audit, and we make sure that everything's done right. And we work with the installer. If we see any problems, we let the general contractor or the construction manager know, and we work through to make sure that it's fixed up. And you get documentation of what went wrong, why it went wrong, how it was fixed, so that you know everything is going to work in the long term. We give you the wording. Basically, we put in the spec that you want an ABAA accredited contractor that uses ABAA certified installers. That's the wording that we sort of want you to put in there. And it gets back to the cementals, independent laboratory. If it's testing of the material, or if it's site testing, maybe mock-up testing, or whatever it is, an independent laboratory will give you a good answer there. Some of the things you could see on the job site, and you don't have to be really picky about these. We got ASTM E783 and 1186, and you can see in the 2 pictures here, the one on the top, we're looking for air leakage. The one on the bottom, that's a spray rack. We're looking at water penetration through there. But, and you can do this really sophisticated, and you can measure the air leakage rate down to the 4th decimal place. I say, who cares? At this part, put that on there. That's poly. You want at least 6 mil, maybe 10 mil poly. Some scraps of wood, seal it to the wall. Take your shop vac that you probably have on the construction site already. Tape it, cut a hole, tape it around there, turn it on. Get some chemical smoke. Go to the party store, or the blower door manufacturers will give you that material. Put smoke in there. Go on the inside. Smoke's coming through. You know you got a leak. Now, do you need to really know the liters per second per meter squared? Who cares? Just seal it. It's that simple. So that can really help you find things. And again, a lot of the mock-ups, you go through this whole process to get that finished. I'm getting the nod that I'm past my time. So we do site inspections. There's a pull adhesion test being done that is done by the installer on a daily basis, and then on the auditor. Wet mill gauge for thickness. We're trying to deal with dry mill thickness because it's not quite as that easy. Looking at some ultrasound, combining a pressure difference using a blower door and infrared can work really, really well. You need a temperature difference between the inside and outside on there. And again, you use your smoke pencil to go around and figure out where the leakage are, and you can get them sealed. Here's the 3158. This is what we're teaching today at South Seattle Community College. We have actually 3 people from South Korea coming, and this is our 2nd course. We have another one in November, and they're coming from all over the United States to take the training on there. Airtightness performance. You're going to get a copy of these slides, so I'm not going to spend a lot of time, but I want to point out that the average building in the United States leaks about 7.9 liters per second. And the code says you should be no greater than 0.2. And in reality, we should be down around 0.5 if we're using a metric. So it just shows that our buildings that we built in the past and even today are a lot leakier than we have. This is a calculator and it's a moisture. I'm not going to spend a lot of time in it, but I ask you to go on the ABAA website and play with it. And the reason why I want you to play with it is we have the 16, almost all the 16 archetypes that's in the code. Department of Energy uses this to determine compliance and so on. So if you're going to do all this work, you need a set archetype. So this gets into the, how it's operated and all the rest of the stuff. In this case, and you can do CFM or you can do metric. In this case, I've chose 5.32 as a base case. As a really leaky building, I want to take it down to 0.15. You do the calculation. And two things to point out here, this number up here, we call that ELA, or equivalent leakage area. If you took all the cracks and holes in that building, it adds up to just over 52 square feet of holes. The part down here, and I'll jump to the next slide because it's a little bit bigger, though that 52 square feet of holes allows moisture in vapor form to get into your building envelope 241,029.5 gallons a year. Do you think that's a problem? My building, I would. And by the way, you can, if you take it down, instead of going 241, you can take it down to 6,000. Now, the size of the building, that's not bad, but you can even do better. And I've just calculated this out. Basically, you've got 2 cups of water going into every stud cavity every day. You really don't want that. Again, whole building. This one in the bottom is a government building in Jamaica, New York. We used 33 fans to do the test on that because it leaked like a sieve, and the test proved it leaked like a sieve. There's some ideas of smoke generated pencils down there. This is simply show if you have a quality assurance program, you can see all the dots with the one exception are below the line. Where you don't have a quality assurance, most of them are above the line and way above the line for air leakage on there. We've added these archetypes, that's now live. We've also added one residential building. We didn't have that before. We had to develop an archetype for that. So almost any type of building that's out there that can be done, and that covers it. Any questions? Somebody has to have one question. Somebody has to disagree with me. That's where it's fun. Okay, I really appreciate you listening. Nobody went to sleep, which I thought was really, really good. And we're going to have a short break so we can switch computers.
Yeah, thanks, Laverne. So we will take a break from now until about 10:30 when we'll start up with our next speaker. There are some beverages over on this side, and the restrooms are out the hall. Thanks, everybody.
Morning, everybody. I'm going to do a little mic test here and also encourage us to kind of come back so we can keep moving. Yes, they are. I figure if I just keep talking over this speaker, they'll have a harder time to ignore me. But it might be wrong.
They're doing a good job of it.
You can't tell it's I know you two. You're the
Yep.
next speaker, Andrew Dunlap.
Yes.
I work for Marcy. You know Marcy well.
Yep, very well. Good to meet you.
I'm on the building for building science.
Cool.
So I was talking to someone going to SeaBEC tomorrow.
I am too. But in between dinner, I was already plotting breakfast for tomorrow. On the way up to ferry over. I ferried over. I live by the meal, if you can't tell.
And you know, I know you all were doing it.
All right, I'm going to get going.
I need 2 seconds before you start, just tell them.
Okay, well, we probably need to get them. So. Yeah. Hey, Nathan. Nathan,
I don't know what you wanted to say.
can you help round them up a little bit? They're not hearing. I mean, they're hearing, but they're not. I hate to interrupt, but we gotta.
Hey, everybody, we're going to get started with Andrew Dunlap's presentation. Andrew is going to go for about an hour and a half, and then we'll hit our lunch break, and you'll have a chance to revisit our sponsors and chat with everybody you're happy to see in person for the first time in 2 years. Thanks, everybody.
So we have some stuff for you. Please take it, please, because if you don't, I have to take it back. So this is just a lot of the different presentations that are out there. Yeah, go ahead. And for whatever reason, when we talk to design professionals, they want a wet mill gauge. And I couldn't figure out why. And then I tried to buy some and they're hard to get. So we got a free one for you, which is to test the thickness of fluid applied as it's being applied. I have my cards up here. And also we have a stick for you. There's a whole bunch of information on this stick in addition to what's on our library and things like that. And if nothing else, if you don't like the material, take it off and now you got a nice stick. But you'll always look at ABAA's name. Thank you.
Good morning, everybody. Hopefully you can hear me okay. I'm probably going to stay up here because I might go around to my computer and mark some stuff up. We'll see what happens today. We're going to flood you with a lot of information. It is an hour-and-a-half presentation. We'll keep the pace pretty rapid. There's a lot to go through. We'll see a lot of different options that we can look at for different enclosure transitions. But a little bit about me first. I got a long list of things that I participate in throughout the industry. I am an architect, so I don't know if Laverne did this, but how many architects do we have in the room? Even Cool, great. So I figured that I'm an architect, I got a license to pick on us. So that might happen throughout, because I do challenge us to do more. Come from a big firm. I've been at Smith Group for over 20 years, straight from college, in our building technology studio, which focuses on exterior enclosures, and a small kind of consulting group within the big company. Smith Group, if you're unaware, is a large AE company, offices around the country. We have some local presence here. Actually, I'm glad to see my colleagues in person. So won't talk a lot about what our company does. Again, primarily an architect that focuses on exterior enclosures and the technologies, and heavily involved in various industry organizations. So without spending a lot of time on that, we have a lot to go through today.